Let us try to understand channel efficiency, otherwise link utilization in go back N protocol or SR protocol. Let's start with this small assumption first. Let's say there is no error in your line. When there is no error in the line, what are you going to do in go back N protocol? There will be a window W, right? And we are going to send all the packets of that window. They will go and you get acknowledgement. That is the idea, right? So we never wait for acknowledgement. We simply send our window. After that, still if acknowledgement doesn't come, then we wait. Correct or not? Meanwhile, while sending itself, if you get acknowledgement, then we move our window and we continue that operation, right? Second thing, in SR protocol also same thing. If there is no error, we send entire window first, correct? Then after that we check whether there is acknowledgement or not for at least one packet. If there is no acknowledgement, then what we do? We simply wait, and if there is already acknowledgement, we move it, right? So go back N protocol and SR protocol behave same when there is no error. But when there is error, so go back N protocol's receiver is behaving in different way than SR protocol's receiver. That's why they get difference. That's why I can say that go back N protocol and SR protocol both are having same channel utilization or link utilization formula. We'll try to have, get that formula. Before that, I would like to ask you one question. Let's say whatever the sliding window protocol you are using, what is the best way? That means, if you really want to use your link effectively, that means, can we achieve link utilization of 1 is the question. In stop and wait, it was very hard to get link utilization 1, correct? Because definitely after sending the frame, we have to wait for the acknowledgement. But here we are not waiting for the acknowledgement, right? Then, so there is a chance of getting link utilization here 1. For that, what we have to do, I will tell you. The optimal situation is this one. First of all, we'll assume some parameters. Let's say transmission time is 1 minute and this propagation delay is, let's say, 3 minutes. Then the question number 1, what is the time earliest I can say where receiver receives the first frame? Definitely after 1 minute the last bit of the first frame will be on the line, correct? Then that last bit has to travel. We have to consider that last bit has to travel this entire 3 minutes. Then so far 1 minute for coming onto the line, the last bit, then 3 minutes for propagation 4. That means I can say if you count time from 0, let's take k as a variable. Initially k equal to 0, sender and receiver are just waiting for the frames. Now sender started sending the frame. When k equal to 1, then this is the time where your last bit of the frame is on the line. That means still your frame is not received by your receiver. Now the importance of k equal to 4 I will tell you. When k equal to 4, that is the time the last bit of your frame is going to come at receiver. Now I can say that entire frame is at receiver. Now this is the time receiver can process it. Now if I assume that processing time is 0, then next what? He will send the acknowledgement and assume that acknowledgement sending time also 0. Otherwise we have to include that also in the formula. Otherwise, let's say assume for simplicity, no processing time, no acknowledgement time. That means once at 4th second I can say that quickly your receiver is going to send acknowledgement. That means he is going to keep this acknowledgement is on the line. How much time it will take for acknowledgement has to come to the line is negligible, 0. Assume that there are only 1 or 2 bits. That's why within 0 second of time they will come onto the line. But this acknowledgement cannot avoid this propagation delay. That's why after 3 minutes it will reach here. So here I can say that's the significance of the 7th minute or k equal to 7 is, this is the time which is earliest your receiver is going to receive, your sender is going to get the acknowledgement. Now remember that k equal to 0 we started transmitting, at k equal to 7 we got the acknowledgement. By that time if you have frames to send, what happens I will tell you. If you can have that many frames, then you will be definitely going to achieve link utilization of 1. I will tell you the reason for that. Let's analyze that in this picture. So t equal to, let's say, 1 minute. That means transmission time I am taking 1 minute for frame, and transmission time of acknowledgement is 0. Only propagation delay is 3 minutes. Okay. Then the first frame is going to come onto the line after 1 minute. Then 1 plus 3 4. At 4th minute it will be here. Then if you immediately send acknowledgement, within 0 time it will come onto the line, because acknowledgement size is, let's say, negligible. Then it won't take transmission time. Then it will be propagated here. 4 plus 3 7. What I want to say is at 7th minute, so you are going to get the acknowledgement that is shown in the picture. Okay. Now see in this picture, first of all we started sending the first frame at 0. That means 0 to 1. This 1 minute duration we were busy sending first frame. After that second frame. Now why you didn't stop? You have maybe enough packets in your window. That's why. How to fix the window? If your window is I can say if window is empty, otherwise if all the frames of that window are already sent, then we keep quiet, correct? That's why we should be careful. What I want to say is, before getting the acknowledgement, we should be able to send lot of frames, correct? Then we should not wait before getting the acknowledgement. For that, your window should have at least these many frames. How many will count? See, 0 to 1, one frame you are sending, 1 to 2, another frame. That means 2 to 3, third frame, 3 to 4, fourth frame. In that way, 6 to 7, seventh frame. If you have 7 frames, you don't really require to wait for the acknowledgement, correct? Now after sending 7 frames, however you get the first acknowledgement, then your window can be moved by 1 frame, then that frame I can send here. But sir, at 8th minute my that frame also will be over, right? That means I had one extra frame now because of moving the window, then I sent it. Then should I wait now? No, you don't really require to wait. The reason, the second acknowledgement is going to come here within 1 minute of time. What is the reason? We will see. See the delay example, let's say there is no errors in the line. That is what our assumption. If there is no error in the line, then the first frame comes at 4th minute, then the second frame comes at 5th minute, because the difference between in the delay in the first transmission and second transmission is only 1 minute. Just observe. First of all, first frame will be sent, it takes 1 minute, correct, in the timeline. Let's say second frame immediately will be started, that also take 1 minute. That's why the delay between first frame and second frame arrival will be only 1 minute. Now what I want to say is, you got acknowledgement for first frame, right? Then you send the next frame, so you move your window by 1 unit and you send that another frame. That takes only 1 minute of time. By that 1 minute, so you will be getting another acknowledgement, then your window will be moved again, then you can send one more frame, then again you get acknowledgement in that way. So from now onwards, this continuous acknowledgements will come with the delay of only 1 minute. Then you never need to wait for anything, right? So what I want to say is, in this process, if you have 7 frames in your window or more than that, then you never need to wait, right? Then your channel link utilization or channel efficiency is exactly 1. Why 1? I will tell you. Are you waiting anywhere? No. How much time you are sending? So you are always sending, right? So whatever the time you are sending the frames, then total time also x only, x by x 1. Otherwise, are we waiting anywhere? If you are waiting, then we do like this. Link utilization is transmission time by transmission time plus waiting time, correct? So that is the formula for link utilization. But here we have only transmission time, but there is no waiting time. Then transmission time by transmission time 1. That is what I want to say. Otherwise, without formula also directly it is visible. You are not waiting for anything. Always you are busy sending, then definitely link efficiency is 1. Remember it. But the only thing is, here there are some assumptions. What are they? There is no error in the line. If there is error, the story is different. Then if you have error, then we have to know the probability of error. That means what is the probability that one packet goes with success, otherwise with failure, right? That probability if you know, then we can again calculate the link utilization or anything. Before that, so first of all, at this moment we assume that so there is no error. When there is no error, and what is the condition to have link utilization 1? Is it always? No. For that, at least your window size, I got one formula for that. To have 100% utilization or 1 efficiency, the window size, the number of frames in this window should be dash equal to, see, up to 7th minute you should be able to transfer the data. Such a way we have to fix the window size. Okay, then I ask myself, why here it is 7? Simple. Because the acknowledgement is going to arrive at 7th minute, correct? That I computed first. Okay, this is important for me to know why link utilization is 1. Now for that, you should have very good window size. If you don't have very good window size, already I told you, if your window size is having only enough packets, so that that size is 3, then that means your window contains only 3 frames. Then you send frame 1, frame 2, frame 3, and after that nothing, you can't send. Then you will be waiting from 3 to 7, correct? This is entire thing is waiting period. Then at that time link efficiency will be reduced. Now we have to generalize it. What should be the window size to have link efficiency? 1. We will try to calculate first of all. After that, remaining story I will tell you. First of all, question is very simple. To have link utilization, the window size should be at least something, right? At least 7 here. But in general case, what should be your window size? That window size should be greater than or equal to what? So finally, I would like to ask one more question. So what parameter is influencing this window size? How you are going to calculate this window size? I will tell you. Since you are going to get acknowledgement in this problem, I will tell you first. Since you are going to get acknowledgement at 7th minute, then in 7 minutes I can say that 0 to 7, 1, 2, 3, 4, 5, 6, 7. You have 7-minute duration, right? Otherwise directly 7 minus 0 is the time. So in 7 minutes of time, what is your transmission capacity? That means how many minutes you require to transfer one frame? 1 minute. Since within 1 minute you are sending one frame, within 7 minutes you will be able to send 7 frames. That means your window should have that many frames. In that way, using the transmission time and this value we can compute it, correct? Example, your transmission time is 2 minutes. Then how many within 7 minutes, up to 7 minutes to transfer the data, what should be the window size? Simple, 7 by 2, 3.5. That means you should have at least 3.5 frames. That means 4 frames. Then only we can send without waiting for anyone or any acknowledgement. So let's generalize it. Okay, let's try to understand how to compute W value. Okay, so assume that let's say T is transmission time, PD is nothing but propagation delay. Now the question is like this. So we should have enough frames until this acknowledgement comes, right? You should be able to send the frames until this acknowledgement comes. So when this acknowledgement is going to come, first acknowledgement, already so many times we have seen, that is first frame transmission time T plus 2 into propagation delay, right? So this much time it will require. Example, in the previous problem it was like transmission time 1 plus 2 into propagation delay was 3 minutes, it was 7, right? So T plus 2 into PD. We have seen this in stop and wait protocol also, right? So one frame rate T, to get the acknowledgement, earliest time is T plus 2 into PD. Now the question is like this. Your window should have how many frames, right? To know that, first of all ask yourself, to send one frame, how much time your transmitter is taking? Exactly equal to transmission time T, correct? Now let me ask, to send some, I don't know how many frames you are sending, but you have to send up to this much time, right? T plus 2 into PD time. So within T time you can send one frame. Then T plus 2 into PD, that is the nothing but time for getting the acknowledgement. So in this duration, how many frames you can send? That's the question. Within T time, if I can send one frame, the transmitter, within this much time, how many frames it can send? That is nothing but, it's a direct proportionate, right? Then we'll write like this, T plus 2 star PD by T into 1. Whenever, this is direct proportionate, like, T time, one frame. T plus 2 into PD, how much time? So it depends on the time. Example, 5 minutes, one frame. 20 minutes, how many frames? 4, right? How do you know that? It's 20 by 5, correct? It's a direct proportionate, that's why directly we write this one on top, this one on downside. We know that, right? Aptitude. So this is the answer. T plus 2 star PD, let's simplify it. Then T can be taken as common. Then it will be 1 plus 2 into propagation delay by T by T, isn't it? So T gets cancelled. It will become 1 plus 2. Already we know that propagation delay by T is nothing but 2a. So I realized that you can send 1 plus 2a frames. That means your window should have at least these many frames, then you don't need to wait. That is one interesting question. So many times they ask in gate, they ask like this. In go back and protocol or SR protocol, whatever it is, then they want to fix window size W, but what is the best window size we can fix so that efficiency will be optimal. Otherwise, link efficiency is 1. Further, definitely, so your window size should be such a way that this much duration you should be able to send frames, correct? Then to send this much duration, then the number of frames should be 1 plus 2a. Your window should have that many frames. If you have less than that, you should wait, correct? So now I got W value. W equal to 1 plus 2a is the best possibility. Of course, you can have more than that also. If you have more than that, not a problem. It should not be less than that. So W greater than or equal to 1 plus 2a, then link efficiency is 1. Remember it. But it is not compulsory. That means, everyone may not fix W value like this, correct? What if W less than 1 plus 2a? In that situation, what could be the link efficiency? Try to understand. Finally, link efficiency is 1. Only in what case you have enough frames in your window. And what would be the enough frames in your window? 1 plus 2a. Correct? But what if you don't have that many frames in your window? Mistakenly, some people, I don't know why, but they kept W value which is less than 1 plus 2a. This case we did not cover, correct? Then what happens? What will be the efficiency? We'll try to calculate. Okay. Let's see what happens when W less than 1 plus 2a. I take t 1 minute and propagation delay 2 minutes. If that is the case, and window size 3, very less. So the first packet is going to come onto the line at 1 minute. Then 1 plus 2 3. That means at third minute you are going to get the message at receiver. Now receiver is immediately sending the frame. So 3 plus 2 5. At 5, that acknowledgement will be received. Now we are getting acknowledgement at 5. Before that, window size is 3. Then only we can send 3 frames. After that, these 2 minutes you are going to simply keep quiet, right? This is, I can say, wastage. Because of that, utilization cannot be 1. Now if you see one more thing, when you waste time here, then you don't send frames this side, right? When you don't send frames here, again you started sending frames from 5th point, because the first acknowledgement you got here. Then again you send a frame, then again you get acknowledgement here also. You see, you get acknowledgements continuously. 3 acknowledgements continuously you get. That's why you will be able to send again 5, 6, 7. That means 3 frames again. Here 1, here 1, here 1, right? Once you send 3 frames, then again you have to keep quiet here and here. Can I say one thing? So the same process will be repeated. First of all, you send frames, then you will wait, then acknowledgement comes. Then when first acknowledgement comes, then continuously you are going to get acknowledgements. Then you do the same thing again and again. But after some time you are waiting, right? Because of waiting, there will be waiting at receiver. That's why you can't get acknowledgements also consecutively. So there will be a delay here, and again you get acknowledgements, again you can begin. So I can say that there is a cycle. What is that? Sending phase, I can say, waiting phase. Sending phase, waiting phase, same thing. If you see this picture completely, you understand that there is a sending phase, after that waiting phase. So I can say that channel efficiency is nothing but what is the time you are sending, right? Sending phase time, duration of sending by duration of sending plus waiting, correct? That's a simple formula for your, I can say, efficiency formula, right? Let's do that. So how much time you are sending? Simple. Since we are sending 3 frames here, right? 3 into transmission delay. Let's generalize it. If your if your window size is W, then W frames you are going to send, right? Sending time is nothing but W frames. See here, W frames. How much time they take? Assume that transmission time is T, fixed length frames. Each one takes T time. In that time, we are using the link, but total time is W into T, correct? Plus, what is the waiting time? Waiting time is nothing but how much time you are waiting. If you want to know the waiting time, we have simple calculation. What is that? Actually, acknowledgement is going to come at exactly 1t into 1 plus 2a. Let's calculate that. When are you going to get first acknowledgement? That is important. First acknowledgement. You get first acknowledgement at t plus 2 into propagation delay. Correct? Remember it. Equation number 1. So that means what? This is the total duration. I am calculating the total duration, right? So here sending time plus waiting time is nothing but total duration. So the total duration formula is nothing but this is exactly equal to the total duration equal to the time to get the first acknowledgement after sending the first frame. That will be t plus 2 into propagation delay. Let me tell you one more time. If you see the picture, you understand that here you are sending exactly when are you busy? You are busy when you are sending the data. How much time you send? W into t. Out of how much time? Total time is this sending time plus wasting time. But we know that sending time plus wasting time is exactly equal to, see this, right, this one 5, right? Why it is 5? That 5 is nothing but the time when the acknowledgement comes. That's why the time when acknowledgement comes is t plus 2 into propagation delay. In this t period, w into t is nothing but the sending time. Let's simplify it. W into, if I simplify it, t by t plus 2 into propagation delay. If you don't understand why this formula is correct, then go back to stop and wait protocol. In stop and wait protocol, what was the efficiency? You are not sending W frames over there, correct? You are sending only one frame. Send a frame, T time. After that, wait for the acknowledgement. But waiting time here also same as stop and wait. In stop and wait, what was the waiting time after sending the frame? 2 into propagation delay, correct? So that's why total time will be transmission time plus 2 into propagation delay. In the same way here also same thing, t plus 2 into propagation delay. But in this period of time, we are effectively able to send W into t. That means your channel was busy this much time. But in stop and wait, W value 1 I can say. That's why it is 1 into t by t plus 2 into pt, right? Now let's simplify it. Then already we simplified it. Then if I take t common, it will be t 1 plus 2 into propagation delay by t. Already I told you propagation delay by time is a, right? Then tt will be cancelled. W, this is nothing but 1 by 1 plus 2a, right? This is the channel efficiency in sliding window protocol. W by 1 plus 2a. Let me write it. W by 1 plus 2a. Let's compare. Stop and wait protocols channel efficiency is 1 by 1 plus 2a. But sliding window protocols channel efficiency when there is no error is when W, see this is necessary condition. That means you don't have a lot of frames in your window. That means W less than 1 plus 2a. In this scenario, the answer is 1 W by 1 plus 2a. Sir, what if W greater than or equal to 1 plus 2a? Then we know that we have lot of frames, so we can always send without waiting for any acknowledgement, right? Automatically they will come. So at that time efficiency is 1. We have seen it already. So this is a story about channel efficiency in go back N protocol and SR protocol when there is no error. But when there is error, let's assume that let's say packet has error with probability P. Then what will be the channel efficiency? What will be the channel efficiency in go back N protocol, and what is the channel efficiency in SR protocol? They are definitely different. Why? Why they are different? I will tell you. In go back N protocol, when there is error, then we send all the remaining packets again, correct? Example, you are sending 10 frames 1 to 10. If second packet is error, then we have to send third packet, fourth packet. Example, let's say error is at second packet. Then if you send 3, 4, 5, 6, 7, 8, 9 by sender, then all the packets at receiver side will be discarded. Then you have to send that 3, 4, 5, 6, 7, 8, 9, of course 2 also, again one more time. That's why efficiency of go back N protocol definitely is not better than SR protocol. Why in SR protocol we have advantage, we'll see. So in SR protocol, when example let's say same second packet is lost, then we only expect that second, receiver is going to expect only second packet. So he will buffer 3, 4, 5, 6, 7, 8, 9, right, 10 up to. So that's why I can say that definitely SR protocol is better than go back N protocol with respect to channel efficiency, right? If a line has error, what happens, we'll see. In that case, we will see what is the link utilization of SR protocol and go back N protocol. Assume that let's say packet has P probability to get error. That means either it is going to be lost, otherwise it is going to be damaged. Further probability is P. In that case, what is the link utilization in SR protocol and what is the link utilization in go back N? We will see. In link utilization, if you see in SR protocol, let's revise. When there is no error, it was 1 when W greater than or equal to 1 plus 2a. When W less than 1 plus 2a, it was W by 1 plus 2a. Let's observe that. Now, did you remember example in SR protocol, what we are going to do is whatever the packet has error, we are going to retransmit it, isn't it? Now let me ask one question. In stop and wait protocol, we calculated expected number of transmissions for one packet. That means when you send a packet, if it has an error, we will resend, isn't it? In SR protocol also, of course we are sending a group of packets, but whenever a packet in that group has an error, we are going to send it back, only that one, right? That's why SR protocol and stop and wait protocol both are same. But the only thing is, in stop and wait protocol, we are only going to send one packet and we are waiting for the acknowledgement. But in SR protocol, we send some group of packets window exactly, and after that we are waiting. Apart from that, there is no difference. But in go back in protocol, if some packet is lost, example 7th packet is lost, then again we are going to send all the subsequent packets, right? But in SR protocol, whatever the packet has error, we are going to send only that. That is the only difference. That's why I can say that stop and wait protocol and SR protocol are almost same. Now in SR protocol, link efficiency we'll see when there is a probability of losing the packets. Example, did you remember, packet has a probability that it is going to lose is P, right? Now number of expected, otherwise expected transmission for this packet is 1 by 1 minus P. Did you remember this value? Whenever a packet has P probability to lose, otherwise to get lost, then the probability of, otherwise the expectation of number of transmission for that packet is 1 by 1 minus P. We have seen it. Okay. Now with that I am going to teach you SR protocol's formula. Since link utilization is 1 when there is no error, since you have error, you are sending a frame again and again, that's why link utilization will be reduced exactly as a factor of number of transmissions. If you send only one packet, you have to send only one packet, and you send only one packet, then utilization is 1. But to send one packet, if you are sending two more packets, utilization will be exactly reduced by 3. This utilization will become 1 by 3. Understand? Example, every day you want to study 6 hours, okay, but you are only studying 2 hours, then your utilization is definitely will be reduced by 3, isn't it? In the same way here also, to send one packet, how many retransmissions you are doing? 1 by 1 minus P. That's why link utilization, whatever the formula you have, 1, you multiply it with this number of retransmissions. Okay, sorry, you divide it by your number of retransmissions, 1 by 1 minus P. Okay, then what happens? You get original now at this moment link utilization. That's why it is 1 minus P. But I can give you the analysis, but analysis part is little bit difficult and it is out of scope. That's why I'm not going to derive them in a formal way as I did for stop and wait protocol. And these formulas whatever we have here, they are little bit difficult to understand. That's why, and one more thing, they are not important for gate. You can ignore them if you want, but for completeness I am teaching them. Okay, so that's why in this video I am just giving you the formulas. I don't give the exact analysis and easy analysis. Okay, I just give rough idea. So this video is specially for remembering the formulas. If you want to know how to derive them, then for that, if I have time, I will create one more video, but that is not compulsory because it is not important for gate. Okay, so remembering the formulas is sufficient. Let's remember them. So how to remember them, I will tell you. In SR protocol, so if your link utilization is 1, then that is going to be reduced by 1 minus P. That means simply divide that utilization by this factor 1 by 1 minus P. Okay, so it will become 1 minus P. Now here also you see your utilization was W by 1 plus 2A. Since you are sending for one packet 1 by 1 minus P packets, then your utilization also will be reduced by that factor. That's why divide your utilization, which is nothing but W by 1 plus 2A. In this case, when W less than 1 plus 2A, it was a formula, right? Then divide it by 1 by 1 minus P. If you do that, you get W into 1 minus P by 1 plus 2A. Okay, but the same thing is not applicable for your go back and protocol. In go back and protocol, what's the problem is, when a packet is lost, then we have to send a lot of other packets. Did you remember? Example, let's say to send, you are sending some 5 packets like this, 1 2 3 4 5. What happened? First packet is lost, then we send 2 3 4 5 again, correct? That's why this number of retransmissions are not 1 by 1 minus P. This 1 by 1 minus p is the different case when we assume that whenever a packet is lost, only that packet will be transferred. If that is the assumption, you get this answer. But in go back n, when a packet is transmitted, if it is lost, we send other packets also. That's why its analysis is difficult and it is different. Now in that analysis, so when w greater than or equal to 1 plus 2a, you get 1 minus p by 1 plus 2a into p. Now when w less than 1 plus 2a, you get w into 1 minus p by 2a plus 1 into 1 minus p plus wp. Remember them like formulas. In the worst case, like with some 0.1% probability, if you get a question in GATE, still you can answer it without knowing the analysis, like how to derive that. Okay.